All right. Good afternoon, everyone. Welcome to this Viceroy Cider virtual seminar. This is our first seminar for the fall 2025 semester. Some of you Viceroy scholars are new, and some of you are returning. You have participated last year or the year before. I would like to welcome you all. We have this virtual seminar every other week for the rest of the semester starting from today. And this will be a great way in which we will see speakers from academia, industry, and government come talk to us on various topics. And this session or this time for the fall semester will feature some new faculties that have joined Washington State University recently. And so today I have the great pleasure of having Dr. Mengyu Liu speak to us. He is a new faculty who joined WSU in 2025. He's in the Tri-Cities campus. His expertise is in cyber physical systems, especially on safety, control, and security. And today he would be talking about cyber physical system recovery from sensor attacks. Mengyu has gotten his PhD from the University of Notre Dame and has an undergrad degree from the University of Toronto. And what he will be talking about today has some of his recent work and things that would be suitable for this audience. I know that as Viceroy scholars, you would be having a number of opportunities also to follow along on bigger things that happen in Viceroy, information sessions and things like that. So I'd like to make sure that you pay attention to those, but the seminar sessions will always be Tuesdays 1:10 to 2 p.m. So I'm very much looking forward to Mengyu, your presentation. I would like to encourage you to take some time towards the end for questions from students. And I'd like to encourage students to be, or all participants to be putting in your questions in the chat as the presentation goes. We'll monitor that and we'll ask Dr. Liu to answer them towards the end. So thank you very much for joining us, and thank you very much for being our kickoff seminar speaker. Mengyu, you can go ahead and get started.
Yeah, thanks for the introduction, and thanks for the invitation to the CISR seminar. It's my pleasure to give a lecture to everyone here, and I'm glad that many of you joined in this speak. Just want to double check. Can you guys see the screen? Yeah. Okay. Cool. So today I'm going to talk about cyber physical system recovery from sensor attacks, and I'm going to briefly show the outline of today's lecture. So there's going to be a short bio of myself, although Asif already introduced me. And I want to cover what are cyber physical systems, we call CPS, and what are sensor attacks and why sensor attacks are critical to CPS. And we are going to the core of today's lectures, how to recover it. We have two categories. One is model-based method and one is model-free method. And I will also introduce some future directions that we can make this recovery more robust and adaptive to CPS and different scenarios. So here is a short bio of me. I'm an assistant professor of computer science and cybersecurity at the Tri-City campus. I get my PhD from University of Notre Dame. I get my master's degree from Syracuse University. And before that, I studied in Canada. I got my bachelor from University of Toronto. And my research focuses on cyber physical systems, CPS, including safety, security, real-time control, and foundation models. Yeah. So like ChatGPT or other video language models. I'm particularly interested in reinforcement learning for control senses with formal guarantees and the CPS securities and adversarial settings. So which means if there's our text. And so then we're going to talk about what are cyber physical systems. Cyber physical systems, CPS, are integrations of computation, networking, and physical processes, where embedded computers and network monitor and control the physical processes via sensors and actuators. So I think this is like the definition, but we can have more like subjective understandings. We can see there are so many applications, CPS applications in our daily life. We can see those drones for agriculture, the water management systems, the smart grid, and on the right middle is the artificial pancreas system. There's a insulin pump and the blood sugar monitor on it, and it will help the patients to control their blood sugar level. And we also have those industrial robots. We have those autonomous cars. All of these systems, these applications are considered CPS, and we are living in a CPS world. And again, there are more and more which are not listed there in your daily life, and many of us didn't realize how big the market is. So we can see that these are some statistics from online, those financial reports that the CPS market will go into $255.3 billion in 2029. And we can see there are 10 industries that's implementing CPS. In 2023, we have those agriculture, aerospace, smart cities, industry 4.0, manufacturing, military, automotive, transportation, utilities, healthcare, cybersecurity. All of these, they're about cybersecurity. And we can see there's a very big share of cybersecurity is about CPS. So, and sensor tech is definitely drawn into this share. And how do we defend our system from sensor tech's one solution is recovery. And let's talk more about CPS because this is our core subject of today's lecture. So I think some of you may heard of the term Internet of Things. That's a similar field to cyber physical system, but it's not identical. I think one core feature of CPS is that we have a feedback loop in the systems. So what do I mean feedback loop is that we have a physical system we also call plant, and it will have its evolution, and the sensors will monitor the states of the system and have some sensor readings, and we feed those sensor readings to states to controller, and the controller will, based on these kind of like states, to generate some control input and forward that to the actuators, and the actuators will act based on that control input, and this will be reflected on the system states. So I'll give you a concrete example. So the actuators on a car is motor. It is motor. And there is a dynamic system, dynamics running on the systems. On the car tells you that how your speed will be affected by the motor, how the engine works. And you can have a speed sensor and other sensors on your car showing that how the internal states of the system, the car is working. And based on this kind of states, for example, speed, we can have a controller. If we are not at our desired speed, we can accelerate or decelerate. So that's how the feedback loop works in a way. And if it's autonomous, everything is happened automatically. And why the feedback loop feature is that important is that it's automatic. And one cost of this automation is that any components in the system being attacked can cause physical failures. So for example, if the sensor, even one of the sensors on the car has been attacked, your car may be unsafe. Or it is not attacked, it's broken, your car may be unsafe if it's autonomous. Okay, and as in this figure, like you can see many common sensors in our daily life. We have those camera, you have LiDAR, you have radar, you have those different IMU sensors. And we can have different controllers as well and actuators. So all of this, they're connected together in the feedback loop and trying to provide this advanced automation for the system. And, unfortunately, although we have those kind of like a powerful features, those CPS are vulnerable. We can see there are so many news that reports that CPS are attacked, and there are even ransomware attacks that a Colonial Pipeline, they paid $5 million ransom one day after cyber attack. And they can see, their attackers keep targeting US grid, electronic grid, and on water supplies, and even Tesla can be attacked. And also drones, those police drones can be attacked from a long distance with only a $40 kit. So this kind of like vulnerabilities really warn us that we should have some procedures or operations or policy strategies to defend CPS from those malicious attackers because they are so easily to be vulnerable. So let's go into one core concept in today's lecture. What are sensor attacks? So we already talked about what are sensors. They're kind of like the eyes, ears of the system, and they can be spoofed. So for example, if the GPS sensor on the car or on the drone is attacked, spoofed, you can see in the figure and GF, maybe they will be operated in a dangerous way. You can be out of road, you can fall down, and if you attack the speed sensor of some motor, it's going to be dangerous for this system. And you can also attack in the thermocouple of the system. It can make the AC in the whole building operated in a normal way. It can be super hot or super cold. So if we alter this sensor information, then it will have direct interaction with the physical parts and it will affect many safety critical infrastructures and it compromises the system safety. So what do we care? Do we care about safety? Of course we care about safety because that's one of the many priorities and even one of the highest priorities in CPS. We care about safety, but safety is not the only things we care about. So for example, in many cases, we can just stay there, do nothing. It is safe, but it's not what we want. We also want it to operate, to have some functionality. And that's one reason why we have to have those recovery procedures. We have to have other solutions, strategies to defend CPS from sensor attacks. So I think one thing I want to spread here is that real-time performance is very important in CPS because in CPS, safety and time are tightly coupled. And you can see in these GIF figures, so this car is very agile, but it is not safe because it has collision with other cars. My vision is that I want to provide safety solutions for CPS in real-time scenarios because if your solution cannot work well in real-time scenarios, sometimes it is very close to you did nothing. What I want to do is that when there are attacks, if we don't make appropriate reaction to attacks in time, the system can be unsafe. Even when there's no attack, if we want to make a car to be very agile, sometimes it can be less safe. So it's kind of like what I want to do is trying to make sure that our system aware the condition and it do the correct and safe action based on the condition. And also in real time, because the safe action, if it's not unreal, sometimes it's not safe. And going back to recovery, so real-time attack recovery is something that I spent about 2 or 3 years in past 5 years doing my research about. And many existing works in CPS research community, they are focusing on attack detection, which means we give a 0 or 1 results, say there is attack or not. But this should not be the end of defend the system, because you should also have some reaction to the attacks after you know there's attack. And if we want to do real-time attack recovery, it's very challenging. The main challenge is, the first is safety. We want to avoid unsafe states for recovery, and we also want to make sure it is on real time. Why we want to do that in real time is that the system should be recovered before some really serious condition happen, which make the system irreparable. And our goal is safely bring CPS back to safe state in real time. So there are two safe words in this. What do I mean safely bring CPS back? Is that during the recovery, you can be unsafe, although your final goal is safe. So if you're doing recovery, but in the recovery process, you're being unsafe, you're totally missing the objective. And that's something that we want to avoid. And here are some papers I published in past 3 years. And many of us, if we have some experience with security, that sometimes reboot solve it. But reboot is not feasible for emergency cases. For example, if your autonomous car is driving on the highway, you cannot just stop there. It's not feasible for this scenario. And this also going back to some comments and statements I made before that. We can be safe if we just stop and stay there, but yeah, for this scenario, you can even not do that. And so basically, if you want to recover the CPS from sensor attack in real time, it's only 2 steps. The first step is stop drifting, and the second step is reduce the cost and negative impact. So let's go over a real example on the left bottom figure. We can see there are 4 subfigures, and we are trying to recover the front car on the bottom from sensor attacks. We can see that there are 2 sets of roads. The front car on the bottom side is driving in normal way, and in the second figure, subfigure B, it has been attacked, and the car started to cross the yellow line, which is dangerous because if it didn't do anything, it will have a collision with the car on the other side. And the first thing is that we should notice that we are already crossing the line, and after that, we stop doing that and getting back to our road, stop at the shoulder of the road. And that's the 2 steps: stop drifting and reduce the cost negative impact. And on the right side is another example. We are flying a drone in an indoor environment, and the top bar is a floor. We don't want it to have collision with the floor. And however, the sensors on the drone can be detected, which makes it misestimate its altitude. Then it is dangerous for it. It may hit it. And for recovery, we need to stop it before the hit happens and save it. That's simple steps or procedures what happened in the recovery. And I will go over it in more details in later slides, but literally, if we talk in simple, it's just 2 steps. So let's go into model-based recovery. So why we call it model-based recovery? If you remember what I just talked about, that feedback loop is one core feature of CPS. And in the feedback loop, in the plant level, we have a system model, which means there are some differential equations. They are the rules or the formulas that the system states and actuations follow. And therefore, if you have this kind of like a modes, you have this kind of math equations, you know how the system will behave and you can estimate what will happen based on what you know. And this is happened in the physical plant on the very bottom. And we can see the bottom 4 blocks, they're just literally the feedback loop. We have controllers, plant actuators, and sensors. However, if you only have these components in the system, it's not adequate for recovery. We also have to have a state predictor, which means we should be able to predict our system's current state, even there's attack. And we should have a model adapter. What does that mean is that because the system is changing and the system can be highly nonlinear, to have a better estimation and have a better recovery performance, sometimes we need to have a local model of the system. So you can imagine a circle. If we want to measure the curve and we don't have a way to draw the curve, we can replace it with piecewise linear curves, lines. Then they are approximate to be a curve in a circle. So that's the spirit and the idea of local model adaptation. And we have those checkpointers and attack detectors, which tells us when did the attack happens. And it also buffers the data from the past, tell us what is the latest trustworthy data points. And time oracle in this framework is tell us that how much time do we have. So this is also very important, as we just talked about. Safety and time are tightly coupled. So we should have something in our mind that how many time budget do we have? And we should finish our recovery by this deadline. If we cannot do it, although we finish the recovery, we're not safe. And we can also see there is a very smart design on the right bottom corner. There's a switch. So basically, we will use in nominal controllers if there's no attack or no attack has been detected. And whenever we have noticed there's attack, the control will be switched from nominal controller to the recovery controller. And that's the core of this work. And here is a brief recovery workflow of this model-based control. We can see on the left the black curve. So these are the trustworthy data that there's no attack happens. We can totally trust it. We can use it for our later use, and we can use it for our control. And at TA time, the attack started to be injected to the sensors, which make the system drift from its target state and is going to unsafe state, which is not desired. However, we can see between TA and TF, this is what we call a detection delay, that we did not detect the attack in the first step after it happened, because it's really hard since many attack detection, they have a thresholding mechanisms that we want to make sure that we don't have too much false positives. So the cost is that we may have some delay after the attack happens, but that's fine because we are not just close to the unsafe set, so we have some time to do response. And after we detect it, we diagnose this, and starting from TR, we recover the system back to our target state. And not only we want to recover it, we also want to maintain the target state set. So that's what we do in the TD and TM. And what we call the challenge is safely recover the system to a safe set is that during the whole recovery process, we don't want our system have any touch with unsafe state set, which is a red region on the top. Okay, and we're going to cover the steps for the model-based recovery to more technical details. So as I mentioned in the framework part, we have a local model adapter, which identify local system models. So this identification can be model-based or data-driven. If we are going to have a data-driven local system identification, we will have a better understanding based on what we have observed in the very short past. And after that, we can use model predictive control to formulate the recovery problem to a quadratic programming problem. What does that mean is that solving recovery. So we're trying to generate a recovery control sequence by solving the problem. The output is that. And everything is obtained by optimization, which means we have guarantee on it. And a tricky part is that by the spirit of MPC that we are not applying the whole control sequence to the system, because if we do that, although we can have better real-time performance, but we will have less precision since we don't know what will happen in the future, or we can only estimate that. But what really happened has a deviation from what we estimated. And this can be calibrated by those observations. We can just apply the first control and we reformulate the problem and resolve it in the next step. And we reapply the first control of the next step, but we just discard the other control generated by this MPC. And because we are solving a quadratic programming problem online, which means it is time consuming, we should have some super efficient algorithm to help us to solve it in this online scenario. Therefore, we apply ADMM based algorithm to solve it in real time. I think is the current state of the art solution for online quadratic programming. And now this will make those kind of like optimization problem solving takes less than, I think, 5 milliseconds, and usually this can be happening in one single control step. And here are some results for this paper. We have done experiments on 3 benchmarks. The first one is a chemical tank. We're trying to control the temperature of this tank. And the second one is a drone, is a high fidelity drone simulation. Is hosted on AirSim. This is a simulator developed by Microsoft, which based on Unreal Engine. And also we have a simulator benchmark on vessel model, which is 1/7 scale. And we're trying to control the speed of the vessel. We can see we have several baselines in the figure. The bottom one is what is showed. Our method in this paper is called MPC, which is a dark blue curve, it always takes the shortest time to recover, and it is smooth and can stay in our desired states, which is the green region. And it can always be finished by the deadline, which is the blue dotted vertical line on the right of the figure. And the right dotted line is show the time that when does the attack happen. Okay, and going back to recovery, we have two categories. The first category is model-based, which we already covered. However, sometimes we don't have those kind of like knowledge about the system. We only have several data we collected from the system. Then we have to try model-free recovery. This paper is published on Real-Time Symposium on 2023. So the framework is a little bit different. Now we have two components in the system. One is called state reconstruction, which is doing the similar things in the previous framework, do the state estimation. And then we have this recovery control calculation, which is basically doing the same thing that the MPC optimization doing. But this time, these two components are replaced by two neural networks, and they are sequence-to-sequence models. So, and again, we also have a nominal controller and it was used when there's no attack detected. And the detector tells us which sensor has been attacked and when the attack started. Here is a brief overview of the architecture of the state reconstructor. It's in encoder-decoder architecture, and it reconstructs the state of the system iteratively. The inputs are time series data, which contains the previous trustworthy states, control inputs, and also the control inputs happen during the attack. And it keeps running until the recovery is over. And one thing to mention about this work is that we don't have too much assumption on the magnitude of the attack and the part of attacks. Therefore, we don't collect attack samples because we cannot make sure they are real. We just collect normal data in the system. We're not learning the attack patterns. We're learning how the system is running in normal conditions. And if there's something happen that which has conflict to which the system happened in a normal way, we know there's something bad happened and we should do a state reconstruction. And here's similar workflow of this recovery and how it happens to do the reconstruction. If we want to reconstruct TA, we use this kind of data, and we reconstruct TA+1, we use this part of data. So this is, we get benefits from the buffer. We're monitoring the system and we buffer the trustworthy data. And we reconstruct TA+2, use this part of historical data. And for the second component in the system, we have a recovery control calculator. It has a very similar architecture to the state reconstructor, but this time the input and output are different. This time we're producing a control sequence iteratively, but only the first control is applied to the system according to the same reason for the MPC part, and it keeps running until the recovery is over. And one thing to mention is that this recovery controller is more agile than the original one, since because recovery, we only have a limited time budget, and this time we are not care too much about smoothness of control and quality of services. Therefore, we want to make sure it's safe and on time, so it usually to be more agile and responsive. And we can, in this one, I can show a demo, and I can show some results from the experiments on the real test lab. We can see there is a car running. We can see they are bounded by the red dotted boxes. And if you are using the original controller to do the recovery, it can recover the system back with a successful state reconstructor, but it is not on time. Therefore, it has collision with some bugs. And if we use our sequence-to-sequence recovery controller, it is faster, and therefore we can get it back in time and we don't have collision. And this want to give us some hints that some insights here, and timely recovery is just as no recovery. So the demo start is on the left is our method, and on the right is the baseline. You can see the recovery happened, and we are safe, but the baseline hit the obstacle. And we already covered model-based recovery and model-free recovery. What can we do for future directions? The first idea it can be recovery-guided attack detection, and the second part is in-context recovery. So going back to the first topic, what is recovery-guided attack detection? So as I mentioned in previous two works, our recovery, the performance of recovery is highly dependent on the precision and performance of the attack detection, because the attack detection need to tell us which sensor has been attacked and when did it happen. And we get too much information from the attack detector, but the attack detector didn't get too much information from the recovery part, which makes us think, okay, this is not good. If they know, the attacker knows there is a recovery strategy on the system, they should know it and get benefits to better coordinate with that. And therefore, we can have a look on the motivating example on the left. If our detector know that there's an attack, there's a recovery controller, it will tell you more information, for example, whether you are recoverable if there is attack happened in later time steps. And this information is very important for administrator and for other components in the system to schedule in advance. And we can see the framework here below is that we can have a residual calculator and a recovery guarantee detector, and authenticator also trying to estimate how recoverable we are of the system. And therefore, we can have a better understanding and assessment of the system safety. And this will also help us to adjust the threshold of the detector, which means that if we want to make your system more sensitive to these attacks, you should also to have a different expectation on the recovery side. Another promising direction for recovery is that for in-context recovery. So now we have trained neural networks for model-free recovery, but they are very agile and may not be possibly usable in all scenarios. It can only cover certain scenarios with very aggressive behavior, but sometimes we may want it to be very aggressive in certain conditions, but not that aggressive in other contexts. So this going back to a question, in different contexts, we should have different recovery control and how to make the model-free recovery have this kind of adaptability. This is not a trivial question. And if we can answer this, we may have better recovery control performance for this CPS. And additionally, since we have different contexts, if the context switching happens during the recovery, how to make sure the system is safe and stable is also an important question that we should ask ourselves and trying to answer in future works. And thank you. This is my seminar talk for today, and I'm open to any questions from the audience. Thank you.
Thank you very much. Thank you. That was very interesting work, and you have left generous time for questions. So I'm going to leave the floor open for any questions. You could unmute yourself and ask if you have any questions, or you could put it in the chat. That will be fine. And while you do that, note that James has put a link for you to fill out the feedback. You can do that right when this is finished, but take the time to give feedback. So anybody has got questions?
Yes, this is Bernie Van Wee, one of the faculty in the CISA program. You showed that the car was corrected in terms of its pathway to miss the obstacle, but it looked like it was diverting too far into the center. If those two lines are a track, was it overcorrecting? And if so, how do you account for that? How do you correct it?
Thank you. Thank you. This is a really good question. So I think you're pointing to this demo, right? To the end of this demo, that is going back too much, right?
Yes.
That's a really good point. So I think for this scenario, we're considering recovery as a cushion. So we're not trying to drive the car back to the road and let it keep running, because it's still under attack and we think it is not the safest way. And therefore, we are trying to provide a cushion to give it a chance to stop at the shoulder of the road.
Okay.
Yeah, so I think that's our purpose here. But definitely, we can also do that if we are trying to drive it back to the center of road. It's just the tuning of the models.
Okay.
So while students keep thinking about question, I've got one for you, Mengyu. You had this chart where you showed the connection with the attack time when it is detected, and then how the recovery would be. And there is unavoidably some delay in when the attack happened and when it gets detected. So if you get good at early detection, right? Would it mean, I would imagine that it would be useful, like if you know it early, it will be useful, but what is the relationship between not only the strategy would use to recover gracefully, but also how much time it would take between the time of detection? So the sooner you detect it, is there anything that you can comment on what that its implication is for recovery?
That's a really good question, Asifo. I think that question is partially addressed in our publication for recovery guided attack detection. So basically, detection delay is a side effect of tuning or choosing the correct threshold for your attack detector. So therefore, if you have let's say a small threshold, you will have a smaller detection delay, but which means that you may have more false positives. But in a very dangerous or emergent cases, I think these things can be overlooked. So if you have a shorter detection delay, which means you have longer time to react to the attacks, and also you have less serious cases that you need to recover, which means maybe you are a little bit further from the unsafe set. So therefore, so I think that's our current understanding to the detection delay to the recovery, and we think this is highly associated, and we want to make sure that the attack detector aware of this condition.
Thank you. So you would be lowering the threshold when to call it an attack, basically, and that's where you would get. But is there other like ways in which the detection could be better other than lowering the threshold? And what I'm thinking of is like, is there any anticipation or something like that that could be useful for attack detection? So you would be okay with false positives to some degree if you have in a safety critical type of application. That will be just a function of lowering threshold. But is there anything like mainly with other things in which attack detection is important, where you could get better at that in terms of finding out, in addition to working with thresholds?
Yes, we have. So we have another publication, I think from 2022 or 2023. I cannot remember the exact year. So we made an adaptive attack detector. What does that mean? That we adjust attack detectors, but it's still the parameters, not the threshold itself. So we want to make sure that it is adaptive to the context. For example, if we are far from the unsafe set, we can make it less aggressive, which reduce the false positive rate. But if we are close to dangerous conditions, then we have no choice. We have to make it very responsive. And so we also have those kind of like adaptive mechanisms designed in the attack detector.
Wonderful. Thank you very much. Anybody has got, we can take one final question, I guess. We have got a minute or so left.
Oh yeah, I guess I had a question kind of about
Go ahead.
the false positives of models. So with like when you developed the model for the car demo, did you take into account like false positives or not, because it's a simulation? And like, do you think it's important to take into account false positives for simulations? What's your thoughts on that?
Yeah, that's a really good question. So false positive is something that really hurts the usability of the whole framework. And we have faced that once, and yeah, it's now showed in the demo. And what we consider the false positive is that there can be two different kinds of false positives. So the first kind, like a false positive, is that there is an anomaly, but it's not attack, but we mark it as attack. And the second kind of like false positive is that there's even no anomaly happen. We just wrongly classify it as uncommon. So that's different. For the first cases, I think we don't care. We're just trying to drive the system back to safe. Either it's a fault or an attack. We should do the best we can to drive it back. For the second part, it's really the main limitation of this work. We don't have too much to do that, and we put all the responsibility to the attack detectors. So if the detectors cannot tell us correct information, of course, it's break the whole feedback loop.
Yeah. Okay, that makes sense. Thank you.
Thank you. Yeah. Good question.
All right. It looks like there is no further question. Thank you very much again. This was very interesting work. And thank you everybody for joining. Make sure to fill out the survey so that we get your feedback. And we will see you 2 weeks from today. And I know there is midterms going on, so good luck with your midterms, those you are having this week. And I will see you in 2 weeks' time. Thank you very much, Mengyu.
Thank you, Asifo. Bye-bye.
Yeah. Bye-bye.